Last session we left off with a population of bacteria that was doubling, and we built a model and did a little bit of work with that. And I want to just reiterate a couple of items on that regarding doubling time. And then we want to continue on today talking about applications using exponential and logarithmic models. So you're feeling pretty good about this. You can use these in science courses, in chemistry classes, in biology, where you're dealing with population growth or maybe radioactive decay in a chemistry course. You can use it in finance and business where you're, say, paying off a loan over time, or you actually have an investment that is growing over time exponentially. And so you use exponential mathematics and the mathematics of logarithms to then build those kind of models to have that understanding. So take this with you into other subject areas and try not to forget it. Okay? So let's go back here to this problem we had the last session. We had 1 billion bacteria, and remember that's 1,000 million bacteria. So it's 10 to the 9th initially, and that I'm going to label as the initial population of bacteria. Oftentimes, for an initial value, we use a little subscript with a little 0 there. Sometimes we call that naught, B naught, is you in the language. So you'll hear other instructors using that vocabulary. We said that the population, we started with 1 billion bacteria, and then someone suggested that we let this population double in 13 hours. So what we did in last session is we built a model as a function of time. Bacteria as a function of time was equal to the initial population, B naught, and then we used a base of 2, and we raised that to the time divided by 13. And the reason we did that for the exponent is because when we put in, well, let's do this first. If we put in 0 for time, that means that'd be the start of our experiment. With 0 in for time, then we have the initial population here times 2 raised to the 0 power. And that turns obviously to 1, and so we end up with that value, that initial value is B naught, which you see right here in the model. At 13 hours, then we have that initial population times 2 raised to the 13 over 13, which is just 2 to the first power, so that's equal to B naught times 2, or in the case of our initial population being 1 billion, then we end up with 2 times 10 to the 9th in scientific notation, 2 billion after 13 hours. The model we had as a graph then is the population as a function of time in hours. After 13 hours, the population is 2 billion, and initially it was 1 billion, or 10 to the 9th here, and then 2 times 10 to the 9th there. And we know from our background with exponentials that the function curves upward. It's not a straight line. It's not a straight line. It gets steeper and steeper the further out you go. Okay, the reason I wanted to start with that today, even though we went through this yesterday, let me just first of all see if anybody has any questions about that. Any questions? Okay. Let's say instead that we knew the tripling time of something. Say the tripling time is, say, 6 hours. 6 hours. So let's do this. Actually, I'm just going to go ahead and put it down below here. Let's say we're talking about apples. The population of apples that I pull off the tree triples in 6 hours. From when I started. That's not a very good example, is it? Let's use money. Okay, let's say we have how much money to start with. Keep it small.
$100.
$100. Okay, so let's say we're talking about money. So let's call it a M function of time and this is an investment. So let's say we start with $100. If we start with $100, that's our initial amount. And let's say we know it triples. Let's not use 6 hours. Let's say, that would be kind of nice. Let's say it triples in
6 years.
6 years, okay? 6 years. Okay? So let's say it triples in 6 years. So what exponent would you put on 3 to build the model? T over 6. T over 6. Because if you put in 6 years for t, then this becomes 3 to the first power, and you're going to end up with $300. Okay? So that's an easy way, if you have a piece of information about your initial population or initial amount, in this case $100, then you can build a model if you have some information about either doubling time, like we did with the bacteria, or tripling time in this case. Okay? So let's take a look. Let me go ahead and put this in here. Let's say we put in our 6 years, and then our amount of money we're going to have is going to be 100 times 3 to the 6 over 6, which is going to be $300. A graph of that, very simple. You're starting with $100, and it's going to grow after 6 years. This is time in years. It's going to grow to 3 times that. Try to get in the habit of drawing your sketches relatively to scale. Relatively to scale. So the graph is going to rise like that to $300 in 6 years, that model. Any questions on that? Not too bad, is it? Okay. Here's a question for you. Let's say we have this money model right here with $100 invested, tripling time known to be 6 years. Let me ask, when is it going to be worth, say, $200? Okay. When will this model be worth $200? Now, if you look at your graphics in here, 200, here, if this is 100, 200, 300, it's going to be right over here, and it's going to be that value of time when this becomes 200, right? This is what we're looking for right there, that value of time. Make sense graphically? Everybody okay? All right. So what we could do is we could just put this in our graphing calculator, couldn't we? Couldn't we? And then we could just trace over until we found the y value equals 200 and read off what that amount of time is, how many years it took to grow to 200. Okay? This would be the same as this if this was 100,000 or 100 million or 100 billion. Okay,
Could
that kind of.
Put 200 in for y and solve it?
Yes, and that's how we would do. And so what I wanted to first of all comment on is how you would interpret this graphically with your calculator or just by a hand sketch here. You know you're going to come up with an answer something less than 6 years. And so now let's go ahead and actually do the algebra like Melissa suggested. We are going to let m of t equal $200. That was our question. When will this grow to $200? So this future value is going to be 200, and we need to figure out this value of time right here. Our model is 100 times 3 to the t over 6 equals now m of t, that's 200. Okay? Everybody with me? So, first step, somebody near the back of the room? Divide both sides by 100. Why do you suggest that we divide both sides by 100? We want to isolate the exponential. Okay, so when you write an exponential equation, you want to now isolate the exponential. So we divide both sides by 100, so we get 3 to the t over 6 is equal to 2. Now somebody in the back row suggests, what's the next step?
Take the log of each side.
Kyle, take the log of both sides. What base do you want to use?
Let's do ln.
ln, natural
Natural
logarithm, base e. So let's take the natural log of both sides of 3 to the t over 6 is equal to the natural log of 2. Everybody okay? Let me put this down. And so then, Kyle, help me one next step.
You pull out the exponent.
Pull out the exponent in front by the power rule. Remember that? The power rule. So t over 6 times the natural log of 3 is equal to the natural log of 2. We now would multiply, there's two ways you can say this or do this. We could divide both sides by the natural log of 3, and that would bring this natural log of 3 off the left side and put it as a denominator on the right. And then we'd multiply both sides by 6, right? But we could also interpret this as, instead of what we could do, is we could multiply both sides by the reciprocal of what's attached to t. The reciprocal of what's attached to t is 6 divided by the natural log of 3. So if we multiply both sides of this equation by 6 over natural log of 3, both sides, remember, that's a little one-step way of isolating t. So then t's actual value is going to be 6 natural log of 2 over natural log of 3. You could, at this point, turn on your calculator and punch this, or what could you do before you turned your calculator on? Just for practice with logarithms. Here's your hint.
Put that in the exponent.
Kick this back up in the power rule, back up as the exponent on the 2. 2 to the 6th is, you should know this, 2 to the 5th is 32. So 2 to the 6th is 2 times 32 is 64. So what we get here is the natural log of 64 divided by the natural log of 3. And what do you get? You better get an answer. Think back here to what we did graphically. We better get an answer something less than 6. And what do you pick up? Calculator.
3.785.
3.785, so about 3.79, roughly 3.8 years. 3.8 years. So here is your exact answers in this format, and there's your approximate answer, about 3.8 years. Okay? So what we did is we built ourselves a simple model by knowing a piece of information about the initial amount invested. Could be $100, $100,000, $100 million, whatever it might be, and it's tripling in 6 years, and then we were figuring out when the amount of money would grow, how much time would it take for it to grow to 200. And there's our result. Okay? So that's a pretty good example.